Whenever you're ready, Kelly. You might have to unmute if you're muted.
Okay, sorry, I have so many windows open. I couldn't actually find the Zoom controls. Okay, so today I'm going to talk about the RSCS student blog. It's called On Circulation. I myself only found out this blog maybe a month ago. I was on Twitter participating in a tweet chat about scientific blogging, and a couple of past bloggers who were on Twitter and saw this tweet chat alerted me to the fact that RSCS already has a blogging website set up and ready to go. So a little history about the blog, what I've managed to figure out since I learned about the blog. It started back in 2011 by a team of RSCS students. The blog is hosted on WordPress, which is a free web hosting site. We aim to do regular posts every Thursday by a member of the RSCS HDR community, honours, masters or PhD students. As well as the regular posts every Thursday, we're also considering doing a series of special posts. For example, an On Circulation Alumni Week, where we get past bloggers to come back and let us know what they're doing now. An Honours Week, if there's any honours students interested in posting about their research, it'd be great to post them all within a week or two. And also we're considering doing an RSCS interview week, where students can interview their supervisors, postdocs in their lab, or anyone else in the RSCS department that they'd like to interview and feature on the blog. We're also promoting the posts on Twitter and Facebook. The Twitter and Facebook handles are at the bottom of this slide. If you're using any of these platforms, please follow us and share any posts that you find interesting. So currently there's 6 of us who are organising and running this blog. Even though the 6 of us are kind of the core On Circulation team, this blog belongs to everyone. So please, if you have suggestions or want to contribute, just contact one of us. As you'll see, we're spread across many of the research groups. And next year we will be looking for 1 or 2 more people to join the team, particularly for the research groups that aren't represented. So see how you go for the rest of the year with your workload. And if you can think of any posts you'd like to contribute or you'd like to be part of the organising team, let us know and we can pop you on the roster starting in January. So you may be asking, why would you want to contribute to this blog? You're not getting paid to do it. It's going to take time out from your lab work or your thesis writing, but we actually think it's quite valuable and could be quite useful to you now and in the future. First of all, you can practice your writing. If you don't particularly like writing, you feel like you're not good at it, maybe English is your 2nd or 3rd or 4th language, writing a blog post is a good way to practice your writing, to get feedback from some of us on the team or from your fellow students if they want to edit the post for you. And it's fairly low pressure. You're writing for a general audience. You're not writing for, for your thesis or for a publication. It's a way to share your research and your passion with the public and with members of your family and friends who aren't part of the university. You can, write your blog posts, send it to them, pop it on your social media, and they can all have a look and see what you're doing, and it's written in accessible ways. That's a good way to promote any publications that you may be co-author on. You can write a summary blog post of the publication, attach a link to the publication, and this may, direct more people to the publication than who would have otherwise seen it. It's a good way to increase your visibility around the world. Because of COVID, we're not traveling to international conferences and events. However, this blog can travel all over the world and be seen by literally anyone who has the internet. And it's also a good way to answer selection criteria if you go for a government or industry job. Or a science communications job when you finish your PhD. A lot of jobs will have the requirement that you can communicate technical concepts in everyday, easy to understand language, and blog posts are evidence of that. So here are some stats from the website. Back in 2013, that was kind of the peak of the blog. They did 234 posts and had more than 30,000 visitors to the site. So far this year, we've done 2 posts and have 1,200 visitors, but we expect that to climb as the year progresses. And in 2014, 15 and 16, they were doing around 40, 50, 60 posts per year, and they were still getting tens of thousands of visitors to the site. Here's a map of the coverage of the blog. So since it was started, it's reached virtually every country in the world besides a few African countries. We've even had one viewing from North Korea. So it truly is an international blog. So ways that you can be involved in the site are obviously to write a post or several posts. If you're a supervisor or a postdoc in a lab, we don't necessarily want you to write posts because it's a student blog, but you can suggest topics for posts to the PhD, masters and honours students in your lab. If you're more of a visual person, we'd love you to contribute illustrations or photographs. If you don't want to actually be on the blog yourself, please promote our posts on social media. And again, if you do want to join the team in 2021, that would be great. And some ideas of what to write if you're sitting here thinking this all sounds wonderful, but I have nothing to say. You do. So you can summarize your research. If you're participating in StuCon, you've already got a 7-minute talk that you condense into 400, 500 or 600 words and send it off to us. Any posters, presentations that you've done in the past or that you would have done this year but can't, great material for a blog post. Or any papers that you've been a co-author on in the last year or so. They don't have to be your first author PhD papers, maybe your 3rd, 4th, 5th, 6th author. Write a post summarizing the work and with a link to the paper, or write a post about the fieldwork that led to the publication of the paper. We'd love to get some explainer or introductory posts about your field of study, particularly in these first few months. It's great to have introductions to our various research groups so that in the future, when we start to write more involved posts, we can link back to them for readers who aren't familiar with the field. And also topical posts are great. I've heard from some of the bloggers from years past that they were always really popular. So if you're an expert on landslides and there's been a big landslide, a volcanic eruption, you know, the wildfires, if you have something to say on those topics and feel that you can kind of expand on what's reported in the media, a blog post on that would be great. And lastly, what next? There is a template that I'll send out to everyone. So if you do want to write a post, just fill it out and send it back to one of the On Circulation team members. We can help you edit posts as well. If you want to write in more than one language, that would be great. You know, if French or German or Spanish is your first language and you feel more comfortable writing in that language, write your initial post in your native language. You can translate it to English and then we'll publish both of them. That'll kind of expand the reach of the post as well. And we're considering having shut up and write sessions for blog post writing as well. So if there are a group of people who know they want to write a blog post but don't have time, we can schedule in an hour or two to work on them. We can then trade our posts with each other, help each other edit them and make this blog something that everyone would really love to read. Just a reminder, these are your 6 members of your On Circulation team. Get in touch with any of us if you have any ideas or questions. And at the bottom of the slide, you'll see our Twitter and Facebook handles and also the web address to the On Circulation blog. That's it for now. It was a bit of a rush, but I managed to get it all in. Are there any questions?
Thanks, Kelly. Any questions for Kelly?
So that's okay. I'll take the silence that everyone's quickly rushing off to write their first posts and get them sent in to us. But yeah, we'd love everyone to be a part of it. So if you do have any questions, feel free to email us. And if not, you'll probably hear from us anyway, because we will come around and ask for posts in person.
All right, thanks, Kelly. We might move on to the next talk.
Mm-hmm.
So next up we have Yankun with prospects of RB as star chronology in the early solar system.
Okay, thanks. Yeah, let me share my screen. Okay, Thanks everyone for coming to my talk. So in this presentation, I will shortly introduce the project I have been working on in the past year of my PhD. So my talk is about the rubidium-strontium chronology used in the early solar system. And I will mainly focus on the background of my research and why we conduct it. So in short, the scientific problem I have been studying is to precisely determine the strontium isotopic composition at the time when our solar system formed. So why do we care about this strontium isotopic composition and why is it important? The story has to begin from the structure of our solar system, which most of you are familiar with. So we have the inner 4 rocky planets and the 4 outer gas planets with a asteroid belt in between. And a very prominent feature we can see here is that all these planets have nearly rounded orbits and they are orbiting the sun roughly on the same plane, which we call the ecliptic. And if we zoom out and look at what's outside the Neptune orbit, so the orbits of all these planets are surrounded by this broad disk-shaped Kuiper belt made by asteroids and comets. And the Kuiper belt and all the planets inside it are enveloped by this huge spherical Oort cloud. So we can see that still the basic structure feature of our solar system is that most of the planetary bodies in our solar system are orbiting the sun on the same plane and making the solar system looks like a flat disk. And this kind of disk-shaped structure is not unique in our solar system. In fact, it has been observed in many exoplanet systems. This picture shows an example. So this is the central star HR 8799 with its 4 planets. And the 4 planets are orbiting the central star anticlockwise in a similar way as in our solar system. And also a debris disk outside the planet B, which is similar to the, our Kuiper belt, has also been observed. So this very common disk-shaped feature of the planetary system is inherited from the star and planet formation process. So in brief, a planetary system usually starts from a giant molecular cloud made of gas and dust in the interstellar space. It can be gravitationally disturbed and starts to collapse. The gas and dust in the cloud envelope fall into the center and at the meantime change the shape of the whole cloud into a swirling disk, which is called a protoplanetary disk. The building block of the planets then form inside this disk by condensation and melting, and the particles inside this disk can collide and stick to each other and eventually grow in size to form the planets. And the whole process is called the accretion of planets. So this is a classic model, but the very exciting thing is that now we have observed almost all these intermediate steps in exoplanet systems. So the big scientific question we are studying is how long time does it take to transform such a protoplanetary disk into the planets by accretion? Studying the time of planet accretion in the disks provides us with plenty of useful information, such as the lifetime of the protoplanetary disk and the formation time of planets, including our own Earth. And all of this can help us to better understand how stars and planets form. The timescale of accretion in the disk can be constrained by telescopic observation of young forming stars or by numerical modeling. For example, the observations tell us that young stars typically lose their disks in timescale between 0.1 to 10 million years. However, these are only rough estimates and can be very model dependent. The precise and detailed time information about planet accretion can only be obtained within our solar system using rock samples. So what planetary rock samples do we have? For example, we can go to the moon to collect samples. We can also send unmanned spacecrafts to sample the asteroids. But most of our information about the solar system come from meteorites, the fragments of other planets and asteroids which have randomly and accidentally dropped on the Earth. We also have a bunch of radioactive decay systems which can be used to measure the formation time of these drop samples, such as the uranium, lead, aluminum, magnesium, manganese, chromium, and the hafnium tungsten decay systems. So for these rock samples and for these very good radioactive isotopic decay systems, we can get very high quality age measurements for these rocks. However, there is some problem when linking the age to the planetary accretion. Many of these rock samples are actually igneous rocks, and their formation typically recurs geological events that happen after the planet is already accreted and formed, such as the cooling and crystallization from a hot magma ocean, or the separation of iron nickel metal from silicate to form the planet core. These ages cannot be simply taken as the accretion of formation age of the planet. So the difficulty to date the planet accretion is that there is either no event during the accretion which can be radioactively dated, or such information has just been erased by the post-accretion geological events. And another problem for dating the planet accretion is Rome was not built in a day, and neither was a planet. The accretion of planets is absolutely not a single event, but instead the accretion from particles to small size of rocks and then into thousands of kilometer-sized planets can take as long as tens of million years. So this means that to study the accretion timescale of planets, we need to constrain both the time before the accretion is started and the time after the accretion is completed. Again, all of these commonly used radioactive decay systems can only provide information for the events occurred after the planet has already accreted and formed. So now we can come back to our research idea and why we need rubidium-strontium chronology. Rubidium-strontium is different from all of these because the main property that controls the chemical fractionation of rubidium and strontium is volatility rather than the compatibility in magma and crystals. This means that this pair of parent and daughter can really tell us something about the events occurred before or during the accretion when the main chemical fractionation was still governed by volatility. So within this whole project, my work is to look at this very early stage before the accretion of all planets. So by analyzing the rock samples formed at the very beginning of the solar system, I can determine the initial strontium isotopic composition of the solar system, and this forms the basis of the rubidium-strontium dating of all other later accretion of planets. So we indeed have got some results and have reported them in the Lunar and Planetary Science Conference. So our finding is that the strontium isotopes seem to be heterogeneously distributed in the at the beginning. So this reason, the reason for this heterogeneity still need to be investigated, and how this will impact the rubidium-strontium chronology will need a further discussion. So I think the time is nearly out, so I'll leave the summary here, and thank you for your attention.
Thanks, Yankun. We've got time up, so we might just move straight on to the next talk. If anyone has any questions for Yankun, just maybe type it in the chat and he'll be able to answer them for you. But next up we have Reading the Reef by Jess Hargreaves.
You see my screen?
Yeah.
Cool. All right. Thanks, Beck. Hi, guys. For those who don't know me, I'm Jess. I'm in the third year of my PhD at the moment. I'm in the Paleo Environment group. However, my work doesn't really fit into the traditional thought of paleo environments, as I tend to work on modern climate change. Today, I just thought I'd give you a really brief introduction into my project, and then we're going to talk about why you should care, first off, and then go into a couple of our fieldwork methods to show you how we read the reef. So my project is based around reconstructing climate variability in the tropical Indian Ocean and using coral over the last 200 years into the last millennium, particularly around the intertropical convergence zone or the tropical rainfall belt. So for those who don't know what that is, it's a zone of intense tropical rainfall across the equator, and it's the primary driver of energy and moisture exchange between the tropics and the higher latitudes. So it pretty much controls rainfall where we are as well. The region receives over 60% of global rainfall, and it has a major influence across the globe. Normally this zone of rainfall shifts seasonally between the northern and the southern hemispheres, and the location of the southern edge of the tropical rainfall belt dictates the location of rain-bearing conditions across Australia. So in Australia, there's 3 varied regions of rainfall, and you can see that in my image here. So we've got the tropical rainfall zone up in northern regions of Australia, and this is mainly controlled by the intertropical convergence zone, so rainfall across this region. Further south, we've got the arid subtropics, and this is a region of really stable, dry conditions. It's where we mostly find the deserts in Australia. And as we go further south, we get into the temperate rainfall zone. So for regions like us here in Canberra, we often receive most of our rainfall in winter, and this is because we get cold fronts coming from the Southern Ocean, and it's mainly controlled by that. So the reason that I particularly care about these interactions, not only does it supply a lot of our rainfall, but there's been a distinct change in the edges of these zones over the last 30 to 40 years. So since the start of the satellite era, we've noticed that there's been a poleward shift in the edge of the tropical rainfall belt. In the southern hemisphere, this is about 1 to 2 degrees of latitude. And it doesn't sound like much, but it actually is quite a lot. So this image here is from the Bureau of Meteorology. The image on the left is the summer anomalies over the last 20 years compared to the mean average rainfall. And the image on the right is the winter anomalies. So you can see that over the last 20 years, so the period of 30 or 40 years, sorry, the period of the satellite era, where we're seeing this shift in the tropical rainfall belt, we're also seeing some of the highest rainfall on record. And this is predominantly in that wet season. So when we're seeing tropical rainfall drift further south. In the winter, we're seeing less rainfall. So some of the driest records driest rainfall records on record. And we approximately see about 40% decline in rainfall across this southwestern Western Australia region. This is really important because this is where most of our agricultural belt is in Australia, and we're seeing increasing drought across this period. Sorry. There are a number of reasons that this shift could be happening, and these are attributed to aerosol changes in the Northern Hemisphere, ozone depletion across Antarctica, greenhouse gas increases, oceanic warming. I could probably go on for a while about these, but one of the main ones that isn't well understood are natural variability and natural changes. And this isn't well documented because we have a very, very short record across the entire globe for this type of anomaly. Mostly tropical rainfall belt extent is measured by satellites and instrumental data, which is so short. And this is where I come in. So what we're doing is we are aiming to reconstruct a high resolution record of sea surface temperature and sea surface salinity, so hydroclimate, from coral records across the southeast tropical Indian Ocean. And that's demonstrated by my map up here. My particular field site is Christmas Island, which is the XI on the image, but we're also using a number of established records across the region as well. And the idea is that we want to create a latitudinal hydroclimate reconstruction for this area. And that's kind of the brief, all I'm going to go into about my project, but you can ask me questions about it later if you want to. But this is a couple of fieldwork methods that we use. So we went out to Christmas Island, so I'm just going to mute this. Went out to Christmas Island in 2018 and did a bunch of collection. This is one of the cores that I'm using in my project. It's about 2 meters tall, so it's about 200 years worth of climate data. So what we do is we use a drill core, and this is Jenny Malaya from the Research School of Biology and Oscar Branson, who was a postdoc here for a while. We go down and we take out the center of the core, and then we can use the proxies within that core, so the elemental ratios and stable oxygen ratios, to tell us about the sea surface temperature and the salinity. We leave a little hole, but we then cover it up so the coral doesn't actually die. And this type of work is really quite laborious, but it's quite a lot of fun, and it's a real privilege to be able to get out there for this type of work. After we get the cores out, they look like this. So we had quite a number of cores. We had 8 corals in the end, the longest of which was 273 centimeters. And that's the core that I work on. The image on the right here is the top of a coral. It's the living section of a coral. So you can see all the polyps at the top here. We take it back to the lab and we do some slabbing is what we call it. So we cut the piece of coral into a number of different slabs, and this is what we use for our analysis in the end. And these, we then X-ray the corals and UV image them so we can see all the banding. And you can see in these images, the lines here are lines of coral growth throughout the years. This is an image of me next to my coral. It's quite tall and quite long, quite a lot of lab work to do, but lots of fun. We then take our slabs into the lab and create ledges. And this is what we do a lot of our milling off, and we mill at a really, really high resolution. So we end up with thousands and thousands of samples in the end. At the moment, I have 5,000 samples, and we'll have another 4,000 in the coming months, hopefully. And then we analyze them. And this is kind of the fun, exciting bit, the bit that I don't have any time to go into. But basically we use stable isotopes, so oxygen 18 and strontium calcium elemental ratios to analyze and understand the sea surface temperature and the hydroclimate of the areas. And that's kind of all I had time for, but thanks for everyone for listening. Questions?
Thanks, Jess. That was really interesting. If anyone has any questions, we've got time for 1 or 2. Leanne?
Hi, Jess. That was a really great talk, and really, I know it's really confined and had to pull that together. Just a suggestion, that little video of you coring is probably a really great thing to have on your personal website later on, just to show people methods, you know, and show people what you're actually capable of, you know, that you've experienced as well. So yeah, just pointing those things out, that sometimes little snapshot videos can be really powerful, and it could also help people, bring people to your lab later on.
Thanks, Leanne. That's a good suggestion. I might do that.
Jordan's asked a question in the chat.
I don't think I can see the chat.
I can tell you what it is.
Yeah.
He says, great talk, Jess. Oh, no, I can't see it anymore.
Okay. What are the other sample sites that you gave? So there's 5 sample sites. One of them is Cocos Keeling Island, which is another Australian site off the coast of WA. Then we have Mentawai Islands, which is Nerily Abram. A lot of Nerily's work comes from Mentawai. Then there's Ningaloo Reef, which is off the coast of WA as well. It's the most southern site that I use. And then Kapung Bay, I think it's called, is the last one. It's kind of in the Indonesian through flow area. So.
Thanks, Jess. We'll move on to Yaji next for her talk on introduction of piston cylinder.
Yeah, thanks, Becca. I will start to share my screen here. Can you see this?
Yep.
Yeah, okay. I will give a brief introduction of the piston cylinder. Actually, that should be start from one of your experiments. So let's start from the book. Here is the most popular original paper cite for the piston cylinder. This one is written in 1960s, and actually the first piston cylinder comes from 1950s. And a couple of people do different designs of different piston cylinder or different temperature and pressure. So for this one, this guy, his design can like arrive the 2000 degree. And we can see the first piston cylinder paper, this one in 1960s. They have a very similar design in our lab. So they have a top ram here, which we don't have this one for our lab's 200-ton piston cylinder. And they have a cooling plant here. And they have a pressure vessel here. And this is a bridge to keep the bottom ring of the piston cylinder. And this is a piston, and this is a cylinder. That's a very important part. All right, let's see their furnace assemble, which is from the middle of here. Right, it's consists of the outer tackle sleeve, which is used for isolating sleeve and the pressure medium. So these two, these two are inserted within the furnace to keep the thermocouple, which is inserted in this hole to isolate it from the furnace. And then we can get the right temperature. And we keep the capsule here. We add the sample into the capsule, and the capsule is made by different metal like platinum and gold. So that's all up to your experiment design. And this is the upper plug which add in here up to the furnace, which is made by steel to keep the electric current. So here is show how it works. So we can see here has a hydraulic pump, which pumping the piston here into the cylinder by like we have a very large drum which have a large area, and we have a piston which have very small area. So we can achieve by pumping this large one and get the very high pressure by pumping this small piston here. So this is what they work to get the temperature heating. So we get an electric isolation layer here, but this one and this one are electric conductive. So we can get a electric current here and heating the graphite here and here. So we heating the furnace, and then we get high temperature in our samples. And actually we have a different kind of heating things like this one and this one. This is for low temperature, and this is for high temperature. We can see that actually here we adding Pyrex glass leaf. That is because you see here, the salt is connected with the graphic tube, which is used for furnace. But while you're adding very high temperature, the salt will melt and it can cause the furnace to break. So we get a grass leaf here to keep them isolated and works well while you adding very high pressure, high temperature on that. So for the different piston cylinder, the average range of the pressure is 5 to 60 kilobar, and the pressure is up to 1,800 degree. And after and during a lot of years, mainly in 1980s and 1970s, people do a lot of things to get the pressure and temperature calculation. So so I will here show you the press X in our lab. Here's the press X. Let's start from the right picture here. For the top one is the distance spacer plant, and this one is the top cooling plate. And you see the tube here is linked with the upper cooling plant here to get water here to get it cooling down of the press vessel. So this is a press vessel here, and this is a bottom cooling plant. So this is the ramming housing. Inside of here, if you still remember the last finger I showed you, here has a ram here to push the piston here, and in here under here is confining ramming housing, which is also like pressing the ram in and press the piston and then get the piston into the cylinder. And if we look details of this press vessel, it consists of 3 different parts. The outside is the soft steel safety ring, and here is the hardened steel supporting ring. And inside of this, with directly contact with your furnace assemble, is a tungsten carbide press vessel, which can bearing very high temperature. So we add in this one on this one, and then we pull this distance plant here, and we get this. So inside of here, we can see this is the bridge, this is the piston, and the piston have a different size of that depending on how much pressure you want. And this is what it looks like of the top cooling plant when we take it off. It's here, and here the plug is linked with this to get the electric current. And this is how we get the distance of the piston. So if you are interested in what happens in the mystery box here, is a hydraulic press like this. And if you are looking our website, we can find that actually we have a very long history of piston cylinder. So I won't spend much time on this, only highlight that the piston I show you is this one, press X. And actually the earliest press is is this one. And it's obtained by Tendru sometime before 1962. But actually that's not a piston cylinder press. You can see there's a multi-level press. So let's continue on the assembles. I draw this for the blog, which is a cartoon to show you like different layers of our assembles. So you can see you load your capsule here, and out of it is a MgO tube, and this is the yellow one is the graphite to keep heating, and this is a glass one to isolate the salt leaf and the graphite furnace. So this photo is passed on our lab. They can show you like when you loading an experiment, how many things you want to put it on. And this is a thermocouple, and how long it needs to get the right distance to get your thermocouple. And this is a thermocouple looks like. We use type B thermocouple, which is by this mantle assemble. So this kind of a thermocouple can keep you, can give you the temperature accurate within 15 degree. So it's quite it's quite enough for my experiment. And they also have different kind of thermocouple you can choose. But this is the most popular one in our lab. All right, that's all from me. And thank you everyone to be here. I'd like to get some questions and comments.
Thanks, Yaji. If anyone has any questions, maybe just write them in the chat for Yaji to answer. Oh, we've got one quick question in the chat. If you wanted to answer that, Yaji.
Sorry, I can't see the.
So Tongfen says, nice informative talk, Yaji. I'm wondering, how do you maintain oxygen fugacity at certain level in the furnace?
Yeah, that's a good question. And for this one, for which one I use, I use a double capsule. I use the outer capsule which made by like you can choose different metal. Like for example, the outer capsule made by palladium, and you get an inner capsule to keep your sample. And beside the outer capsule and the inner capsule, I put nickel oxide as my buffer. Some people also add in like a different kind of material like iron oxide. By controlling the different ratio of iron 3+ and iron 2+, you can know the oxygen fugacity of your experiment. And if you don't need a very high pressure, actually that's not the piston cylinder. You can use the furnace, which can control the oxygen fugacity by the gas fluid. So you can add in two different kind of gas, like carbon oxide and carbon dioxide, so to control the oxygen fugacity. Yeah.
Thanks, Yaji.
Yeah, you're welcome.
So for the next talk, we've got Matthias, whose talk is titled Geophysical Inversion with 3 Monkeys.
Thank you, Beck. I will share my.
Yep, all good?
You're sharing the StuCon program.
Really? I'm sorry. Can you see that now?
No, not yet. Might have to stop sharing. Yeah, there we go.
Yeah? All right, I'm sorry for that.
All good. Thanks, Monica.
All right. All right, so hello everyone. My name is Monica and I am a 3rd year PhD student in experimental petrology group. And today I would like to tell you just a little bit about my project, but I am going to focus on the ChemScan method. So before we go into details, I would like to give you just the general overview about the project I work on. So in my studies, I am mostly focusing on porphyry deposits that are primary sources of few important metals, including copper and gold. But they are related to subduction zones, so their occurrence is actually defined by the tectonic setting. However, not all the porphyries are ore bearing. And in fact, over 90% of them are barren and they don't host any metals. So it is difficult and takes a lot of time and consumes a lot of funds to figure out which ones are prospective and worth further investigation. So through the petrological and geochemical studies, I am actually trying to figure out an effective and hopefully cheap method to distinguish which systems could have the potential to host and form a deposit. And so far, I have been working on volcanic rocks from Papua New Guinea since the beginning of my PhD, and they turned out to be more complex, but also way more interesting than I initially assumed. That's why it took me almost 3 years to finalize this part of the project. And the second part is focusing on igneous rocks from Yerington Copper District in Nevada, in US. So let's move on to ChemScan itself. So the name stands for Quantitative Evaluation of Materials by Scanning Electron Microscopy. And even though it was commercialized almost 20 years ago, it is still considered a fairly new method in our field, and we are still figuring out what is it capable of and what information it can provide. So far we are using high resolution maps and images of mineral and elemental distributions, porosity structure maps, densities of samples, but also we are using quantitative reports. So how it works is that it works with a grid. So we have the sample and we defined the step size, and each one of them is going to be measured for the elemental composition. So it's actually very important to think about your step size before the analysis, because in my case, let's take a look at the first sample. I used a step size of 25 microns, which is more than enough to cover major mineral phases, but anything smaller than that will not be precisely quantified. So just to give you an example, this is a piece of 1.3 by 2 centimeters, and it took me about 1 hour and 15 minutes to analyze. But if we want to analyze the same area with a step size of, let's say, 1 micron, it will take about 24 hours. So you have to figure out what is the most important for your project. These are two other examples of the distribution maps. And the first one includes all the minerals. And what we can see is not just the minerals itself, but also associations. And we can also see some zoning, like in this clinopyroxene, which we can see augite is in yellow and diopside is in blue, but clearly there's some zoning also in olivine. So what you can do, you can select one or few mineral phases. So this is just diopside. So the zoning is much clearer, much more visible over here. So it might help you to find the spots for the further analysis. Now we can also select some elements which can show us the distribution within not only the sample, but also the mineral phases. So we can see which mineral phases are taking which elements into structure. And if we take a look, for example, of this mineral, there is the magnesium and there is iron in green. We cannot really see iron, but if there is some mineral that contains both elements, the color actually is going to be a mixture of both. So we can see there's a little bit more of magnesium in the core of the mineral. And I would like to show you one of the samples that I analyzed and some different combinations of the information that you can get. So of course, this is the mineral distribution map, very detailed. And I also input different types of pyroxenes, of olivine, but also if we want to simplify it, we can just put just groups of minerals. So as you can see, there's some zoning happening here, but there is no zoning over there because I just put it all together as as pyroxene or just olivine. What we can do as well is we can put just the element. So in that case, iron was my focus, and I can see that I know it from this map that this is olivine. But what I can see that is way more. It contains way more iron in the rim than in the core. Then what we can do is we can select some other phases. In that case, it's enstatite and diopside. Again, I can see that there is some rim of the pyroxene around each olivine. This can also be very helpful. You cannot really see much from this because of the step size of 25 microns, but it can also be very helpful to find smaller phases as spinols or sulfides. So if we want to go back to the microscope and actually take a look on the slide, it is much easier to find the point with this map. Together with maps, ChemScan generates also quantitative reports, which I found very useful for my studies, because when I plotted it as a cumulative graph, I can see that some major changes happened once magma had reached a certain point of diffractionation. So I interpreted it to be another magma pulse to the system, and I wouldn't have known that besides if not for this graph. So the software also can provide with some basic chemical analysis, like Forsterite number of the olivine, which reflects the ratio between magnesium and iron, which also tells us a story about the evolution of magma and its stage of diffractionation. So what we would expect if it was a simple system following just the normal fractionation, it was that this number would be just dropping down. But we can see that something was happening here again, because this number just got increased. So that was not what was expected. And it helped me to interpret this to be another major magma pulse to the system. So those bits and pieces of the information just gave me the general idea, not just about the single sample, but actually the whole system, if not the area. So to sum up, ChemScan is very useful tool for petrological studies, but also is widely used in metallurgy, in biological studies, but also in the oil industry. And they can provide very different information that help with the interpretation. And at last, just a few examples of the work environment that I had a chance to experience during my PhD. I enjoyed all of them. So thank you very much.
Thanks, Monica. Does anyone have any questions? Aditya has a question in the chat. If the step size is 1 micron and it encounters a phase smaller than that, does it show a black spot or show the phase which makes up a majority of the 1 micron spot?
It doesn't show, the black spots are actually defined as empty spots. So you would never get anything black, just if it's an empty spot. So what happens is I have a step size of 25 microns, let's say. It can be 1, doesn't matter. So the machine actually is taking, is scanning the sample, covering half of the previous spot. So you would never get anything. It's just a matter of if the phase is smaller than the spot size, you would have a weaker color, if that makes sense. So for example, if you take a look on this map, there are different intensities of red, which means that probably this was a very big grain, but something smaller was just too tiny to quantify it properly. I hope that answers the question.
Tongzheng has a couple of questions as well. The first one is, what is the difference between ChemScan and regular SEM? And the second is, how do you separate OPX from CPX? BSC does not have an information of crystal structure from my understanding.
Yes, so I'm going to start with the second one. So a lot of people have this misconception about the ChemScan, that I am going to analyze the sample and I will get the output of what I have in my sample. Well, no. You actually need to have a pretty good idea about what you have in your sample. So going to the microscope first, because it's just, as you were mentioning, it's just a software, and sometimes the chemical composition can be very, very similar. So there are a few options. You can, if the two phases are very similar, you can do the electron microprobe first, and then you manually input your chemical analysis. So then it's going to be very accurate. Or you try, and sometimes you get very weird minerals that you know they are not there. So that's what happens with the OPX and CPX. I actually manually input the chemical analysis of OPX and CPX from my samples. And what was the first question? I'm sorry.
First question was, what is the difference between ChemScan and regular SEM?
Actually, there is not much difference. It works basically the same. It works with the backscatter electrons. So you get the signal. It's just you record one by one of the certain area that is much bigger than usually with the SEM, as far as I know.
All right, thanks, Monica. We might end it there. We've gone a few minutes over time, so sorry everyone for that. But otherwise, thank you everyone for coming. And I guess see you all again tomorrow morning at 10 a.m. for the second day of StuCon.